Let's zoom back and talk about our thesis as a whole. So we're having too many carbohydrates, too many sugars, we're raising insulin. You talked about the chronic diseases associated with that throughout the body, but let's get into physiology-wise, what's actually happening there.
Every cell in your body has a point in time in its life when it wants to grow, and every cell in your body has a point in time when it wants to burn. Growth, burn, growth, burn. Now, the substrate for both is glucose. Glucose causes growth, glucose causes burning. That's true. But there's a switch in the cell that determines, am I going to grow or am I going to burn? Now, let's do a little thought experiment. Each of us starts out as one cell, a zygote. Okay? Sperm and egg meet, you get a zygote, one cell. Now, that one cell becomes two. Those two cells become four. Four cells become eight. Okay? 8 cells become 16. Okay? You're starting to get to an embryo, right? And there's a doubling and a doubling and a doubling and a doubling. And you end up with a baby. And then that baby has to then become an adult. Okay, so you start out with one cell, and that has to become an adult of 10 trillion cells. So you go from one cell to 10 trillion cells. How many doublings does it take to get from one cell to 10 trillion cells?
Probably less than we think, because when we start getting up there.
It's an exponent, so it's 2 to the what equals 10 trillion.
I don't know. I'm just assuming it's like the penny doubling thing where it seems like it's nothing, and then eventually it's just like flips on a dime. I'm assuming a similar kind of thing.
So how many is it, Jesse?
Okay, I'll say 35.
You're not too bad. Way closer than most people. 41. 2 to the 41 doublings gets you to be an adult. You go from zygote to adult. 41 doublings. Now, some of those will have occurred in utero, and some of those will have occurred after birth. Now, how many of the doublings occurred in utero, and how many of the doublings occurred after birth? So I need 2 numbers that add up to 41.
Okay, I'll say 39 and 2.
Not quite, but you got the right idea. Okay, it's 36 and 5. So 2 to the 36 gets you to a newborn, and then the last 5 get you to an adult. People freak out when you think about that, but I mean, I'll do it for you. Okay, standard baby, 7 pounds. Okay, first doubling, 14 pounds. Second doubling, 28 pounds. Third doubling, 56 pounds. Fourth doubling, 112 pounds. Fifth doubling, 224 pounds. So adult with metabolic syndrome. Okay, so 2 to the 41, 36 in utero, and 5 after birth. Kind of cool, huh? When you think about it. So there has to be a method for the body to use to go from growth in utero to slowing down growth and ultimately burning as an adult. How does that happen? And the answer is a whole bunch of hormones. Okay? But ultimately, there are 3 enzymes in each cell that determine which way the glucose goes. And those 3 enzymes, we mentioned one of them before, PI3 kinase. That's the spigot that lets the glucose in. The second one's called AMP kinase. That's the fuel gauge on the cell to tell it whether or not it needs to burn because ATP is running out. And if ATP is not running out, then you won't send it, and you might send it to growth instead, the glucose. And then the last one is called mTOR, mammalian target of rapamycin. And what that enzyme does, it determines whether the cell's ready to divide. So if your cell is in burning mode, your PI3 kinase is low, your AMP kinase is high, and your mTOR is low. Conversely, if you're in growth mode, then it's the opposite. Your PI3 kinase is high, your AMP kinase is low, and your mTOR is high. So you have burning, you have growth. And those three enzymes determine which way the glucose is going to go. Is it going to growth or is it going to burning? Okay? And it can't do both. It's got to do one or the other. Okay? Think of it like a cord of wood. Okay? You can do two things with the cord of wood. You can burn it in a fireplace for heat, or you can build furniture. But you can't do both. Okay? One or the other. And these three enzymes determine which way it's going to go. So if you're in growth mode, you grow. If you're in burning mode, you burn. And the three enzymes have to be in synchrony with each other in order to do that. What if those three enzymes are not in synchrony? What if they're off? What if they're not doing exactly what growth or burning would dictate? So basically you've got three enzymes, two valences, high-low, or on-off. That means you have 2 to the 3 permutations. You have 8 permutations. One of them is growth, one of them is burning. That means there's 6 more. Every one of those is a chronic disease. It is the dysynchrony of those 3 enzymes that lead to the chronic disease. And so the question is, what did that? And the answer is, that's our environment. That's our nutrition. Turning those on or off. And it turns out those 3 enzymes are all kinases. They're all phosphorylatable. So that's what a kinase is. You get phosphate put on it, and it changes the enzyme, changes the activity. Okay, so kinase can turn on, can turn off based on its phosphorylation status. Well, what determines the phosphorylation status? The metabolic status inside the cell, reactive oxygen species, which your mitochondria make. So when your mitochondria make ROSs, it tells those 3 enzymes to go one way and not the other way. So everything is in concert as long as those 3 enzymes are doing what they're supposed to all at the same time. When they fall out of synchrony, that's when you end up with disease. And those are determined by what the mitochondria is doing. Fix the mitochondria, fix the whole thing.
I had asked about insulin and its contribution to the chronic diseases. Connect that piece with what you just said.
Well, so when your mitochondria are not working, the insulin's going to basically have to go up in order to divert the glucose away from the mitochondria, the pyruvate away from the mitochondria, to go to something else. So the pyruvate can be used in the Randle cycle to make proteins, or it can be used in the de novo lipogenesis to make lipids, or it can be used in the pentose phosphate shunt to make ribose for DNA. Okay, so you can grow the cell. You can grow the cell so it can divide. Okay, now you don't want the cell to divide if you're supposed to be in burning mode. That's what happens in your coronary arteries. You get coronary artery, smooth vascular muscular growth. That's what makes the coronary artery that much thicker and stiffer. And then it's a lot easier for a plug, for a thrombus to come, plug it up, and now you have a heart attack. Okay. In addition, that insulin's a growth factor, and so when the insulin goes up, it causes glands to grow. And when glands grow, much more chance for a tumor to develop. So there's your breast cancer. Okay? And insulin causes diversion of energy in the brain away from neurons because the insulin receptors are on astrocytes. Okay, and so they end up storing glycogen, and when they store glycogen, that starts the phospho-tau thing, and that's been associated with Alzheimer's. So the more insulin, the more growth, And the more growth, when it's not supposed to grow, the more risk for disease.
If you enjoyed that clip, you're going to want to head over here and catch a full episode. I'll see you over there.
Insulin is the bad guy. I can't say it any simpler than that. Yes, glucose is bad too. I'm not saying it's not. Insulin's worse. Insulin is associated with all of the diseases.